Okay, and then it is going to be also depending on the wavelength. So for the 254 nanometer, even with the lower energy density, the surviving fraction is much, much lower. And then for the 308 nanometer, it's longer, higher energy density in terms of same surviving fraction compared with the 193 nanometers. So actually, this means that not, or the shorter is more powerful so that it can damage the, cell. But as you can see in this example, the 254 nanometer is longer than 193 nanometer. However, it can damage the cell more significantly. That is because the DNA is actually absorbing light at the 250 nanometer range, which is shown on here, 240 to 260 nanometer. And also, when you look at the energy density, sister chromatid exchange per cell is also happening here. And then this sister chromatid exchange per cell means that how much of the repair is happening in the cell. So if you see the higher number here, then that means that there is more repair is going on, which means that there is also high chance to be a mutagenic for the cell. And then that is also much higher in the 254 nanometer, which is shown on the left with the square symbol, compared with the 193 or 308 nanometers when you are increasing energy density. So to talk about the sister chromatid exchange, let's look at the cell cycle. So cell cycle is following this S, G2, and then going in the G1, and the G0. G0 is cell cycle arrest. And then G1 is basically chromosomes are going to be duplicated. And then S will be each of the 46 chromosome is going to be duplicated by the cell. And then go to the G2, the cell is double checking the duplicate chromosomes for the error. And then if there is any error, then it starts to repair itself. From the G2, it goes on for the mitosis and the cytokinesis, and then differentiated into two cells. So from here, the sister chromatids is shown on the left here. So that those two are the basically chromatid, but same each other. And then as this G2 into the cytokinesis step, you can see those sister chromatids are going to be separated each other and then going into the other side. And then here you can see the sister chromatid is moving against each other for the opposite pole. And then the right side is also showing the same process shown on here. So on the top, it shows the homologous chromosomes, and then it goes through the replication process. And then you can see now you have a sister chromatids, so basically identical chromatid each other. And then it will be separated and then mixed together, which is shown at the bottom after mitosis process. So this sister chromatid exchange, or simply SCE, is the exchange of the homologous stretches of the DNA sequence between sister chromatids. And why this is happening? Because sister chromatid exchange occurs normally in cells during mitosis, or in other words, cell division. But when the cell DNA is damaged by genotoxic agents, then the rate of sister chromatid exchange increases. And then it is thought that SCE is an attempt by the cell to fix the DNA damage caused by genotoxic agents. In this case, the UV light. So more potent genotoxic agent is going to generate higher rate of the sister chromatid exchange. But too many damage events eventually will cause the cell to give up and die. So here, showing another example, there is an old chromosome, which is the original one, and then the red one is new chromosome, which is replicated from the original one. And then when there is something wrong, then sister chromatid exchange is happening, as you can see each other. So let's look at the cytotoxicity of the UV radiation further. So excimer laser causes the less mutagenic compared with the mercury lamps. The reason is that proteins in the cytosol observe radiation at the 193 nanometer so that it can protect the DNA in nucleus. So 1 micromole of the cytoplasm can observe 60% of the incident radiation. However, there is report that 193 nanometer absorption causes 253 nanometer fluorescence emission, so that it can cause the damage on DNA. So we have seen that between 240 and 260 nanometers wavelength can damage the DNA. So we want to reduce those area. However, when you are using 193 nanometers, it absorbs the energy. The cytoplasm absorbs the energy. However, it generates 250 nanometers of fluorescence. And then this fluorescence is basically directly damage the DNA. So that, no, not good. So here's a summary of the photoablation. The main idea is that direct breaking the molecular bonds by giving high energy of the UV photons. And then observation is very clean ablation. And then, but during that photoablation, actually you can hear some sound, and also you can see some kind of visible the fluorescence, like mostly bluish color. And typically, the laser used for the photoablation is excimer laser, such as the argon fluoride, krypton fluoride, or xenon chlorine, or xenon fluoride. And typical first durations for the photoablation is 10 to 100 nanoseconds, so much shorter than the microsecond, not to cause the thermal damage. And typically the power density is going to be 10 to 7 to 10 to 10 watt per centimeter square. And the special applications of photoablation is on the refractive corneal surgery. So using the LASIK or LASIK. However, these days, the femtosecond laser is actually more and more becoming popular for the eye, the corneal surgery. Okay. Okay, now let's move on for the plasma-induced ablation. So let me share a new PowerPoint. So we have been discussing about the photochemical interaction and the thermal interaction and the photoablation. And then now we have only two interaction mechanisms are left. So those two are plasma-induced ablation and the photodisruption. And then actually those two are very highly related to each other. And both of them requires to have a very short time. So micro, nano, and the picosecond range with a high power density. So this photo here is basically the captured time photo of when you use the high power but short duration time laser to the surface of the tooth. And then you can see something, came out. And that is actually the plasma spark. So like that. This plasma is actually called as the optical breakdown. And this optical breakdown is happening when the power densities are greater than 10 to 11 watt per centimeter square in solid or the fluid. And then in the air, that even has to be more higher so that it should be greater than 10 to 14 watt per centimeter square. So by having this one, very clean and well-defined remover of tissue without evidence of thermal or mechanical damage can be achieved. So plasma-induced ablation is also called as a plasma-mediated ablation because this ablation is caused by plasma itself. And then if it has a more mechanical process, then it is called as a photo disruption. So when optical breakdown happens, it can be causing multi process. The first one here is shown as a plasma formation. And then second one is shock wave generation. And third one is cavitation. So plasma formation can be happening in either gas or liquid or solid. And then this plasma is simply basically ionized state. So when the light is focused in the very, very small volume with a very, very high density of the power, then it can cause the plasma. And the plasma is basically making the state, the material to be ionized. So making positive and negative like that. And then plasma is going to be spatially confined within their focal volume because the plasma itself cannot be easily formed. It will form only in the focused area with a focal volume with a very high power density. So about 70 to 99% of the optical breakdown is shown as a plasma formation. But it can also make a shock wave generation. So that is going to be about 1 to 5% of the optical breakdown energy. And when the shock wave is generated, it will cause the high pressure gradient at the front of the shock wave. And then this shock wave is going to move very fast. So supersonic speed, which means they're faster than the sound speed. When the optical breakdown is happening in the kind of liquid or kind of very soft tissue, then the cavitation can happen. For the cavitation, the vapor is going to induce the mechanical stress, and then successive expansion and the collapse will happen during the cavitation process. And they will be corresponding to about 15 to 25% when the optical breakdown happens. And if this cavitation occurs close to the solid boundary, then it will also cause the jet formation. And then this jet will form during the collapse of the cavitation. So here, the right side three, shock wave generation and cavitation and jet formation is basically photo disruption because mechanically it can actually give a damage to the tissue. For the left one, plasma formation, this is called a plasma-induced ablation. So basically making the tissue to the plasma state, and becoming plasma state, it will be ablated and then going away. So either plasma-induced ablation or photodisruption, both of them are causes the tissue ablation. So you can take a look at this video. If you do not hear the sound, then you can visit this YouTube website. So let's watch. So optical breakdown. And you can see the optical breakdown happens in the very, very small focal point when there is a very high power density is happening there. You see in the air, when there is a laser, it's kind of focused in a very small volume. The air, which is the nitrogen and oxygen, that is going to be becoming the plasma state. And then it shows this kind of bluish color of the light. Okay. So here are examples of the plasma-induced ablation. Here, the top is showing the cross-section of the cornea when the laser was having 30 picosecond and the pulse energy was 200 microjoule. At the bottom, it shows the tooth. And then with the 30 picosecond neodymium YRF laser, with 1 millijoule of the pulse energy, which is 5 times higher than the top. And then it cut 1 by 1 millimeter square area with the pattern size. So PIA is a plasma-induced ablation. And also, as you can imagine, the first step is basically the formation of the plasma, and the plasma is not actually generated in any time. It has to have a specific condition. So that is basically plasma-induced ablation condition. That is the local electric field strength, E, which is going to determine threshold when the optical breakdown happens. So the threshold for the PIA can be basically thought as electric field forces. So applied electric field is going to force the molecule to become ionization or the atom to be ionization. And then that is basically plasma state, which is also called as a fourth fundamental state. This electric field E and the local power intensity I are related each other in here. So you can see that the intensity, power density is going to be square of the electric field relationships. So typical threshold intensity of the optical breakdown is 10 to 11 watt per centimeter square when there is a picosecond pulse. And then that intensity, it corresponds to the E as a 10 to 7 voltage per centimeter. So this electric field is comparable to the average of the atomic or intramolecular Coulomb in electric field. So basically this electric field should be actually same or higher than the atomic or intramolecular Coulomb electric field. Then it can break down. So within a few hundred picoseconds, a very large free electron density with a typical value of 10 to 18 per centimeter cube. So within 1 centimeter by 1 centimeter cube, there will be 10 to 18 number of the free electron is going to be generated when you are giving very short pulse with a high focused, with a high intensity of the laser beam. So this plasma generation from the high intensity electric field is called also as a dielectric breakdown. And then this optical breakdown is emphasizing that the UV or visible or IR light are strongly absorbed by the plasma itself. So since once the plasma is generated, as you have seen it in the previous lecture, when the energy density is higher than some certain level, then the ablation depth is not increasing anymore. Okay. So here is the some experimental results. So Pradine measured intensity of the ruby laser pulses transmitted through the sodium chloride, which is the salt. And then the laser was TEM00 mode, so that basically a simple circular shape of the light and a 0.3 millijoule pulse energy. And then the pulse duration was 15 nanoseconds and focused by using a lens, and then the focal length was 14 millimeter from the lens. So here on the top, A is showing that the pulse shape is basically maintained, which means that the light intensity in this case was smaller than threshold. However, when you look at the B and C, you can see the rear part of the pulse was strongly observed. So it should be same as the top. However, you can see at certain time later, it basically goes down to the 0. And here, it started a little bit late, but very quickly also going away when the laser pulse was generated. So this can happen when the light intensity is beyond the threshold of the plasma generation, so that the generated plasma will observe the succeeding the laser pulse energy, so that the laser pulse energy here is it looks like a kind of 0 because of the absorption by the plasma itself. So this kind of cartoon is showing about the initiation of the ionization. So either using Q switch laser, which can have a nanosecond laser, or using model light laser, which can generate picosecond to the femtosecond laser. So for the Q switch nanosecond laser, since it's not very short pulse, so that it can cause the thermionic emission, which means that generating the heat and the high temperature can actually eject the electron, so that this is going to be the free electron, not bound to any atom here. For the mode-locked laser, it can have a very short pulse, so that it can make the multi-photon ionization. So not a single photon comes in, but multiple photons are coming in within very short time, so that they can cause the ejection of the electron, and then becomes the ion here. So here will be positive ion. And this free electron generated either from thermionic emission or multi-photon ionization, that is going to be the initiation of the plasma. So once free electron has been generated, and then if you are continue to if you continue to irradiate the laser to the same spot, then this photon energy is going to be observed by free electron. And then this free electron will have a very high kinetic energy. And then since it has a very high kinetic energy, by hitting with another molecule or another atom, and then it can make electron in the atom or molecule to be ejected again, and then becoming the ion state. So the free electron can make two free electron, and then these two free electron can also make four electrons here. So it is called as an electron avalanche growth. So from the single free electron to the multiple free electron later, as the area, the focal volume is continue to observe the laser energy. And in this process, can be explained as an inverse of the Bremsstrahlung radiation. So Bremsstrahlung radiation is basically means that by giving a very high kinetic energy, and then once the kinetic energy suddenly kind of stopped or very slow down, then the radiation can come out, which is the either X-ray or the photon can come out. But here is opposite, so that by giving the laser, the electron can gain more kinetic energy so that it has enough energy to kick out the electron in the atom or molecule. So initiation of ionization, let's look at this one. So the thermionic emission is basically releasing electron due to the very high thermal energy. And the multiphoton ionization, it happens when the coherent absorption of the several photons are happening. And then in that case, it can provide energy which is enough for making atom to be ionized. So due to the requirement of coherence, this multiphoton ionization can be achieved only during the high peak intensities. So as in the picosecond or femtosecond laser pulse. However, Q-switched laser pulse, which is the nanosecond pulse laser, can provide higher plasma energy and also plasma temperature compared with the mode-locked laser pulse, which is the picosecond. That is because of the threshold energy for the plasma formation from nanosecond pulse is much higher. So in simple way, when you are using longer pulse, you can still make a plasma. However, to generate plasma in the longer pulse duration, you need to have a much higher power density. But when you have a very short pulse duration, which is a picosecond or femtosecond, in that case, the threshold of the plasma generation energy is lower, so that you can actually generate even lower the power density compared with the nanosecond laser. So when you make optical breakdown by using nanosecond pulse, then that optical breakdown will have a higher energy compared with the picosecond generated optical breakdown. So this nanosecond pulse caused optical breakdown will have a higher energy, so that those extra energy can initiate some other non-ionizing side effects, which is the photodisruption. So let's look at the electron avalanche growth. So we look at the free electron generation, and then those free electron needs to do something to make more friends. So a few of the lucky electrons can initiate the avalanche effect. which means that the accumulation of the free electron and also ions. This free electron can absorb the energy from the photon, and then it can accelerate. So means that it increase the kinetic energy. The accelerated electron is going to hit with another atom and then making ionization itself, so that there will be another free electron. So now single free electron becomes two free electron, and then 4, and then 8, 16, and then 32, 64, like that. So each of them with a less individual kinetic energy than the initial electron. What I mean is that once single free electron is absorbing energy from the laser, so that it has a high kinetic energy and the hitting the neutral atom, and then making free electron and the ion. But those generated free electron will have a lower energy compared with the coming in the initial free electron. So that you need to have some continued supply of the energy, so that the second free electron will also gain energy, and then it can be accelerated. So this free electron can observe incoming photons and then accelerate itself and striking other atoms and then releasing two more electrons and go on and on and on, which is the avalanche process. So the basic process of the photon absorption and the electron acceleration can happen in the presence of atom. Is called as the inverse of the Bremsstrahlung. So ordinary Bremsstrahlung is basically when the electron is passing near to the proton, and then because of the attraction force, it loses, it slows down, and then slow down means that losing kinetic energy, and then the difference of the kinetic energy can be coming out as electromagnetic radiation, which can be a light or the X-ray. But for the process of the inverse Bremsstrahlung, that's opposite. So you are getting the energy from the laser, and then you are increasing the kinetic energy of the electron. So let's stop for today here, and then we will continue on this Thursday. Okay, so see you soon.